Welcome to E Squared Emporium for all things AP Psychology. Today we're going to talk about actually running an experiment, and we're going to get to all the building blocks that you need for scientific research. So, an experiment allows investigators to isolate different effects by manipulating an independent variable and keeping all the other variables constant. So, how do we begin an experiment? Well, we're going to use the scientific method to collect and analyze data. Science requires that we observe and experiment. So we're looking for reliable data that can be repeated, and we're looking for just the facts. So it starts with a theory. A theory is a possible explanation. I think that if I get more hours of sleep at night, then I think I'll have a better chance in my class tomorrow. I think I'll remember more items on my test. Then you have to go look at all the peer-reviewed or published studies that may there have been sleep studies, there have been studies on memory and what improves memory. So these are empirical studies or peer-reviewed studies, and this will form a solid foundation for the theory, and then you'll create it into a hypothesis. A hypothesis is a prediction. It is a cause and effect with an independent variable and a dependent variable. So a theory becomes a hypothesis when it organizes your observation and it implies a predicted outcome. Now, you might be wrong, but at least you're trying to give a predicted outcome. So now my theory says less than 8 hours of sleep will impact the ability to remember test items. And now it's become a hypothesis that I can go out and test. So the hypothesis is written as H with an exponent of 1. That's the hypothesis. For a hypothesis to be scientific, the scientific method requires that we could actually test it. So it has to be based on previous theories, and it has to be something that we can now go run a testable study, a testable prediction on. So caffeine makes me smarter. That is not a hypothesis. We would say adult humans given, and I would say X amount of caffeine, right? Adult humans given 50 milligrams of caffeine will navigate a cognitive maze faster than adult humans not given caffeine. So that would be a much better, much stronger hypothesis. How do we remember the scientific method? We remember it with Homer. Now you can remember the ancient philosopher Homer, or you can remember Homer Simpson, however it helps you. Homer. So hypothesize, operationalize, measure, evaluate, replicate. So it's an acronym or a mnemonic for us to remember the research process. And again, here's just another way of looking at the scientific method. I think Homer's a little bit easier for us to remember, but it's saying the same thing here. Now, the null hypothesis, null means zero, empty set, nothing. So we write this as H with an exponent of a 0. So H with exponent 0 is the null hypothesis, which just simply says we were wrong. So all of our famous inventors were wrong a lot, and so they had to accept the null hypothesis a lot. It just means you didn't prove your hypothesis, and you've got 499 more tries to get the hypothesis correct. It just means you need to change something about your variables, or something else happened in the study that you didn't expect, and you have to accept the null hypothesis. And the null hypothesis in statistics means that there is not a strong enough difference. It could have been chance. It could have been confounding variables. So the independent variable did not make a difference 95% of the time or greater on the dependent variable. And we'll talk about statistical significance another time. So some examples here. Cats did not show preference for a certain food based on shape. I don't know that cats care if your cat food is shaped like a fish or not. Plants did not grow based on light color, and age did not have an effect on musical ability. So those are examples where you just have to accept the null hypothesis. Sometimes it's a little frustrating if you've been doing your research for 10 or 15 years and you have to start back at the drawing board, but that's just a part of the scientific method. Now, a falsifiable hypothesis is something that could be disproved. So there were things that we believed in the 1800s that we have disproved. So if we said something like aliens don't exist, well, the minute that we actually can prove that aliens do exist, it is falsifiable. If we claim that all frogs are green, but then we find that there are purple frogs, which there are, that would be a falsifiable hypothesis. We used to believe that all swans were white, except for when we went to Australia. Then all of a sudden we saw that there were black swans and the Natalie Portman movie. So then we'd have to say, oh, that was falsifiable. So the independent variable you can write as IV. It is a variable that is deliberately manipulated. It is the new thing that we are introducing. We're changing the light, we're changing the food, we're changing the drink, we're adding a drug. It is the thing that we are changing. But you have to keep everything else constant and consistent in order for the study to work. The dependent variable is what we depend on. We depend on the dependent variable to tell us if the independent variable really made a difference or if it was just chance. So this is the variable we would measure before and after we've given the independent variable. And the dependent variable needs to be stated exactly what's being measured. So for instance, how many words can I memorize? Well, study me before I have caffeine. How many words could I memorize? And then give me an equal list, not the same list, but an equal list of words of the same difficulty level after I've had my caffeine, and I'll bet you I can remember more words. So the dependent variable would be the number of words. The caffeine would be the independent variable. It's the thing you're introducing as new to see if it made a difference. Now we'd have to make that scientific to get 95% that it happened 95% of the time with 95% consistency and repeatability, and then we could say that that was a real study. So here's another example. If we have a lot of distracting noise in the classroom, somebody's playing a trumpet in your ear while you're trying to study, that's the independent variable. And would it have an effect on your ability to recall new information that you're learning in AP Physics? That's the dependent variable. And yes, it would. It would absolutely have an impact. So again, we depend on the dependent variable to tell us if the independent variable actually made a difference, or was it just chance? All right, we're going to do some more practice with this in class. So we remember this on the axis chart as dry mix. Dry mix. Let's go through, what does dry mix stand for? So D, dependent, R, response, Y, axis. So the dependent or the response goes on the y-axis when we chart this. Mix, M is manipulate, I is independent, and X is the x-axis. So the part that we manipulate is the independent variable, and it goes on the x-axis. That's how we remember this as dry mix. The operational definition is very important. Our variables need to have clear measurements, like more caffeine helps me remember stuff is not very clear. So it is clear, it is precise, it is quantifiable, which means it is data. It is a number, it is a percentage, it is a statement of the exact procedures of operation. So I could hand it to any other researcher in the world and they should be able to follow my clear, precise, quantifiable operating procedures, and they should be able to get similar results. So we want an operational definition that is clear so the study can be replicated by others. So down here at this hypothesis, overexertion leads to exhaustion. We need to operationally define that a little bit better. How do we define overexertion? Well, it's working more than 12 hours. How do we define exhaustion? Well, it's extreme tiredness, which we could study with cortisol levels, or we could study with a survey. And it's incapacitating to work anymore, right? So we have to make that really clear. So here's an example. After X amount of less sleep, a person will recall 3% less. See how I will operationalize the X, and we've operationalized how much less you'll recall. So we know that the average person needs 8 hours of sleep. You need so many REM cycles per night. So if we gave you 10% less sleep, right, or we could give you, say, 7 hours of sleep, or we could give you -2 hours of sleep, whatever we make X, we've operationalized it. So that's what we need to say, 10% less sleep or 2 hours less sleep. That would be operationalizing this hypothesis. This is all for, sorry, replication. So we want to be able to repeat, 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 repeat. Like the Milgram study, which we will learn about, has been done in multiple countries with both men and women going on from the 1960s into 2022. They're still practicing it and we're still getting the same results. So if you replicate it, it makes it more reliable. It means the results can be repeated. So anyone could repeat the experiment. You will get similar results no matter how often you repeat it. This means we can trust the study. It means the study is reliable. So would you want to take a headache medicine that only worked some of the time? No. You want to take a headache medicine that you know is going to help your headache each and every time. It is repeatable. It is reliable. It is consistent. That's what we mean, replication. Validity is another term we need to know. Is your research valid? Does the research actually do what it claims to do? Sometimes we set off to do a research study and we think we're studying sleep, but we were actually studying noise level or we actually had something else. So the test is valid when it measures what it's supposed to. And here are two examples where we use the wrong tool for the job. Say I'm trying to measure volume of milk in a glass, but I brought a ruler. A ruler is not the right tool for that measurement. Okay. Using a fork to try to eat soup is the wrong tool for that application. So we have to make sure our test is correctly measuring what we think it is correctly measuring. So all of our great efforts, but we bring the wrong tool to the game, we're not going to have any results that we can actually verify. So low ecological validity has to do with not in a real life situation. High ecological validity means it could be a real life situation. Okay, so there's the validity of the test. Is the test actually measuring the right thing? And then there's ecological validity, which is the ecology, right? Ecology means the environment. That's what the word means. So in the environment, like this little boy sitting at this computer in the picture that has a C on it, that's not generally real life unless he walks around with that machine in front of his eyes all the time. That's not generally real life. So it has low ecological validity. It cannot be generalized to real life situations. It cannot be generalized to playing on the football field. So standing in line at the grocery store, the picture at the bottom, that could be generalized to real life situations. So if we do the study in a subway, in a hospital, in a school, in a corporate office, it has a lot higher ecological validity. So it's the right study, it's the right test, and it's in a naturally occurring environment. So quick little game here. Let's look at these four pictures. Does this look natural, right? A, does that look natural? That's a really early study, and it doesn't look terribly natural. It's occurring in a lab, and it looks very forced, right? That's not naturally occurring. B, I don't know that I've seen all of these posts like this normally when I go to the desert or to the beach. I don't know that I normally see all these posts in the sand. That doesn't look like it's terribly natural. All right, C is the little boy again staring into the machine. And D is people walking down the hallway, probably at a university. That could be natural. Out of all of these, D is the only one that looks like it has ecological validity, like it could actually happen. Construct validity is, again, are you testing the right thing? So sometimes we think we're testing one thing and we're testing something else. So anxiety, self-esteem, persistence, these are all just examples of psychological constructs or concepts. It's a single concept, but it's really complex. How do we measure self-esteem? How do we measure anxiety? How do we measure your persistence and your grit and your resilience? So researchers can't measure them directly. We could give you a test, we could set you up in scenarios, we can infer from the way that you answer, but it's very difficult. So we have to make sure that there's validity in the way that the test is constructed. Is the test designed correctly? Am I measuring the correct thing? If the test doesn't measure the concept that it's claiming to measure, then your conclusions will be invalid. Somebody can come along and say, yeah, but you're not really testing that. So for example, a self-esteem test, but it's actually measuring depression or happiness. It's not actually measuring self-esteem. This has actually happened before. That's a real life example. So for example, sticking with self-esteem, it's a very complex set of variables. Do you have a feeling of security? Do you have self-confidence? How do you see yourself? How are you feeling that day? Are you having any pain or any issues that day? Are you feeling competent that day? Do you have a sense of belonging that day? Is the sun shining? There are so many things that could go into your self-esteem. Your favorite team just won the game the night before. You got a really good score on a test. All of those things boost our self-esteem. Those are, what did I say, 7 variables? And so you could be ending up testing so many things other than self-esteem. So that's what we mean by construct validity. So we want our studies to be reliable and valid. So this very first arrow here and this target, well, it's reliable because you got the same answer every time, but it's not valid because it completely missed the mark of what you were trying to test. The second one has very low validity and very low reliability because you're all over the place. You missed what you were trying to test and it wasn't reliable. The next one also is not very reliable and not very valid. You missed the mark and it's kind of all over the place. Only this last one here is both reliable, meaning you got the same results every time you tested it, and it's valid, meaning you hit the mark of what you were trying to test. You created a valid test. Yeah, go you. You did it. Yeah, you. All right, that is the end of part 1. So please make sure you go ahead and watch part 2.